Hi, welcome to the Noise Path. In this episode, we're going to take a look at another viewer-sent item. This is an Agilent Electronic Calibration Module. This one is up to 9 gigahertz. It's actually not a very high frequency one. You can now get these things almost to 100 gigahertz. It's a 2-port version. It still has the old connector at the top, but it does have USB, of course. So what you do with this is you just simply connect the USB port directly to your network analyzer. The instrument will recognize this, download the information from what is on the EEPROM of this one, and then you can then perform your calibration. Now, before these ECals were available, people were just calibrating using different standards, a calibration kit. Here's an example of one. This is quite a modern one. This is a Keysight A55638. This is a 50 gigahertz calibration module. You can see this has V connectors. Very nice, it's brand new. And this particular one has 3 standards on it, an open, a short, and a load. And it's missing a through. There's no through on this one, but you can just simply connect your 2 cables together. That would be your through in that situation. You'd have to then take into account what the delay of that through is, for example. So every one of these calibration kits is going to have some imperfections associated with it, and sometimes they come with a disk that tell you what those imperfections are. What is the additional capacitance or inductance or so on these different ports. So when the instrument measures these, it takes those into account when it does the final calibration. So here's another example, one that's type N. This one has a through on it as well, so is all nicely connected to each other. You can get these, of course, separate, but having them all connected to each other kind of makes sure you don't lose them. It's very convenient. You can also get them from other manufacturers. Of course, here's a Roden Schwartz one. This one goes up to 8.5 gigahertz. We use these a lot with the Z and L hybrid instruments. Here's one higher frequency, 26.5 gigahertz. Again, 2-port. You can get them into 4-port configuration as well. I don't have one of those here in the lab. So this is broken and we want to take a look at it. Now, the major advantage of having an electronic calibration module is you only make one connection. So you connect this to your network analyzer and that's it. You don't have to connect and disconnect to jump between the different standards. For something like this, you're going to have to connect each port to each of these separately, do the calibration, do it again on the other port, and so on and on. And that not only wears out your cable, but it also takes a long time and it moves things around. And it's going to be very difficult to perform like metrology grade calibration. The ECal module only has one port connection, but it also has some disadvantages. First of all, it's quite a bit more expensive than a coaxial calibration kit like the one you saw. And at the same time, it has some power limitation because it has some switching inside done in solid state, typically done with pin diodes in order to switch the different standards. And that makes this have some maximum power limitation too. In this case, this is 20 dBm for damage, but slowly it's going to become not as good in terms of its calibration functions. At the same time, you can store the exact response of this on an EEPROM inside of it. So it will download that into the network analyzer, and then there's no doubt what the calibration standard specifications are. It's perfect, especially when these things vary with respect to each other. You can even use these as a calibration standard for something else. You can use it as a transfer. So once you know exactly what S parameters this has, measured against a perfect, let's say, calibration kit, you can then use this as a transfer as well. So I want to see how it works on the inside. I also want to show you the block diagram of the first patent written on these so you can see how it is on the inside. It's very straightforward. Of course, the difficulty is in implementing these. And then we're going to take it apart and see what it looks like. So here's a very simple figure from the original patent that was done on the electronic modules. And I think the company that made this original patent was bought up by Agilent at some point. So if you look at this, the structure is essentially exactly the same. All we have is a front-end switch here and a front-end switch here that allows you to switch between the standards of the through, open, short, and the match, the load. Now, there may have been some changes and updates and improvements over the years, but the principal operation remains the same. There's also an interesting attenuation through piece as well. So of course, in principle, this looks very nice, but in practice, you're going to have to implement these switches with very little parasitics. You're never going to get a perfect through, short, and open, but you don't have to because you can measure the exact response of this and then store that response inside of the electronic calibration module and then download that back onto the network analyzer. Now, you can have these to be anywhere you want neither. If you put them into some really strange locations on the Smith chart, you will run into some problems getting a good calibration anyway. That's a subject for a different video perhaps. But this is kind of what we expect to find on the RF side, and how it's implemented will be very interesting. These are almost certainly pin diode switches. Now, I don't know if the unit that I have uses exactly this principle or not, but that's part of the fun. We're going to take it apart and find out how it works. Okay, so let's see what we have here. There we go. Very nice. So it is a multi-board construction. In the center, we have a Cypress USB microcontroller IC. These used to be quite popular. This gives you USB interface as well as a 8051 base microprocessor in the middle. A couple of op amps around. We have some bus switching over here, maybe to control whatever's at the bottom, and a big flash memory chip. So all the characteristics of the standards, which are all stored in here, are going to be stored in this flash memory. That way you can just download them back on the instrument. We're going to take this apart a little bit more to get to the bottom board, but all the fun stuff is going to be in here. And here's a nice board-to-board construction here. And of course, for things like this, no expense has been spared. The money is not the issue for these things. It was just to build them to work best and have good compatibility with future instruments. So this is for the USB interface and the memory. And you can see at the bottom, we have the other type of interface, some kind of parallel interface with all the switching required to control this module. Now at the back of this, the module has its own pins that poke through these individual sockets, and this is how they make a connection. So this is not soldered to the board. We can disconnect it and totally remove it. It's nice because if something like this dies, then they can just simply replace this as opposed to replace everything else and then reprogram the flash memory with the new settings. So we have to disassemble this a bit further. So here's the footprint of that module. Look at how many filter components there are on this. Every single pin has to be perfectly filtered out so there is no noise going back into the instrument. Very nice. And here's the back of it. You can see this, where those pins sit, and the module itself, of course. Look how beautiful it is. Yeah, look at that. Very nice. And these things, again, must have cost a fortune initially when developed. So this is soldered in place. I'm just going to use my soldering iron to slowly remove this so we can look underneath it without damaging it too much. And all the pins are going to remain intact. Now this obviously needs EST protection. I'm not doing any of that here because this is dead, but very excited to see what's inside of this. Well, I went ahead and removed that plate, and there's something else underneath it, but this one is only screwed in. So maybe that's for additional hermetic sealing, or that is just so that no one can open these screws so easily, and that way they can maybe keep some of this stuff underneath secret. And here we go. Wow, look at that beautiful piece of engineering. Look at this, no expense spared at all to make this, but I think this is going to deserve some more microscope investigation. All right, let's take a look at this and take it one step at a time. Here on the very left side, we have one of the ports coming in. You can see that there is a ribbon bonding to this trace. Here's a capacitor that decouples the entire structure. If you look at this capacitor, you can see there's a mom capacitor. That's metal oxide metal type of capacitor. These are interdigitated right underneath it. This is actually a hybrid structure. A capacitor at the top, that's the large one, and a smaller one at the bottom in parallel. This increases the frequency range of operation of this capacitor because it works beyond the self-resonance of the first one. This is a common technique done even inside of integrated circuits to improve the frequency range of capacitors. And then we hit our switches. So these are solid-state switches. Here's one over here. These are most likely pin diode based. You can see it has one input, and then it has two outputs. There's a ribbon bond on this one, a wire bond on this one. So if you follow this path of switches, you can see all the different states of standards that are built into this ECal module. At the right, we go to the top, we go to another switch, and at the very top, you can see we have a line over here terminated. This is probably our short standard. And then on the other side, it switches into this one. This looks like a thin film resistor. It could be our 50 ohm load. This could be the load standard. And then on the other side, it goes into another trace, into this switch. Now this trace has this thin film resistor connected to it as well, and I think it needs that in order to bias the other side of this pin diode potentially, because the other side of this one is already biased through this big metal ground plane over here, but this one doesn't have that because this is part of the through standard too. So as a result, we have this resistor there most likely to bias it, which is wire bonded away. So therefore we have short, load, and this is just a connection. Now if you look at this, at the bottom side of this switches, there's nothing connected to it. So they're most likely using this for the open standard. So they basically switch this path to the bottom, and then you get your open. And then if you switch it to the other side, you go onto this line, and we can follow that line further and see where it goes. There we go, we hit the middle, and in the middle you can see exactly what was in the block diagram. Here's our through standard, and here's that 3 dB attenuation coupling between the two ports. So there's some thin film resistors there. So there's a through path and an attenuated through path, quite interesting. And then you follow it on the other side, you get the exact symmetry, you get the mirror image of it on the other side again. So the through line comes back over here, and then it goes back to this. So there's the same biasing network over here, same open port here, same short standard, same load, capacitor, and to the other port. Yeah, very nice. It's completely symmetric across the entire structure, and yeah, it's beautiful. And it's obviously all done by hand. It's one of the reasons why it is so expensive. And you can imagine how hard it would be to take this to a higher and higher frequency. This is only 9 gigahertz. Imagine building this at, at 67 gigahertz, and those things are quite expensive and obviously far more integrated than this is now. This is quite old. But it's really beautiful to see how it is all put together, and nice to see that it follows what I think is kind of like the block diagram. So at least the operation is fairly obvious when you look at it from that point of view. And there you have it. I hope you enjoyed this quick video, and thanks always to the Patreon supporters who make all of this possible, and to the people who send these microwave components in. Please do check the Patreon page. I'm going to try to do a couple of new things in there, and hopefully we'll be posting that soon. And if you have any questions, let me know in the comment section.